So
Yes. Arrhenius and activation energy.
So in this case, in a reaction, when we study a reaction, we have to study some aspects regarding using as a parameter. So temperature is also a parameter for studying a reaction. So the temperature dependence on the rate of a reaction is a very important topic to study. By Arrhenius equation, we get the equation which tells us the relation between the rate constant and the temperature. So what Arrhenius equation provides, that the equation is K equals to A into e to the power minus EA by RT. So this is the equation, Arrhenius equation, and in this case K is rate constant, A is frequency factor, and EA is activation energy. So this is the relation between activation energy and rate constant by Arrhenius equation.
Yes, how to determine activation energy from Arrhenius equation, and what the difference between Arrhenius and integrated Arrhenius equation?
Okay, so the differential or integrated equation for Arrhenius equation is d ln k dt equals to EA by RT square. This is the integrated equation, or not integrated, this is the differential equation. And another equation which tells us how to determine the value of activation energy is log K2 by K1 is equals to 2.303 R by 1 by T1 minus 1 upon T2. By this equation, we can determine the value of activation energy from the experiment.
Yes. What the graph of log K versus 1 upon T in Arrhenius equation?
Okay. So we know the equation K equals to EA by A into EA by RT, and if we take log, so it will be ln A minus EA by RT, and then if we plot ln K here and 1 by T here, so the plot will be like this. This is ln A intercept, and slope will be minus EA by R. सर आप ठीक से देख पा रहे हैं या फिर वहां पे रिफ्लेक्शन आ रहा है?
नहीं सही, थोड़ा साइड में है लेकिन कोई नहीं दिखाई दे रहा. Yes. Yes, but the unit of Arrhenius equation exponential factor.
Okay, so the e to the power EA by RT, this part of the Arrhenius equation is basically unitless, because the unit of EA is joule per mole, and joule per mole, and the equation, the unit of R is joule per mole per Kelvin. and the unit of T is Kelvin. So when we use EA by RT, then joule per mole per Kelvin into Kelvin. So everything divides itself and it becomes 1. So this is why e to the power EA by RT, this part is unitless. So this is why the unit of K is equals to the unit of A, which is our pre-exponential factor. In this case, whatever the order the reaction is, the unit of the rate constant will be the unit of the pre-exponential factor.
Yes. What the relation between Arrhenius equation exponential factor and activation energy and Arrhenius relation? Any formula?
Sir, one equation is there, which is the integrated form of Arrhenius equation, which is d ln k by dt, and EA equals to RT square into d ln k dt. This is the equation. You are you talking about this equation?
Yes. Yes, what the main purpose of this formula?
From this formula, we can predict the value of activation energy theoretically. Because this formula is a fundamental formula for Arrhenius equation. From this equation, we can deduce or we can determine the actual Arrhenius equation, which is K equals to A into e to the power EA by RT.
Any drawback and limitation of activation energy, Arrhenius equation, Arrhenius integrated Arrhenius equation, Arrhenius equation, pre-exponential factor. Yes.
Okay.
Any drawback
So
limitation?
in this, when Arrhenius equation, we are talking about Arrhenius equation, then we assume that according to Arrhenius that the temperature is independent of activation energy, and we also maintain the rule and think that activation energy is not dependent or independent of temperature. But in case of some reaction, there the graph of ln k versus 1 by t, according to Arrhenius, this is looking like this, but some of the reaction shows the graph like this. So this type of behavior is called as non-Arrhenius behavior. So when non-Arrhenius behavior is shown in any process, then we introduce or some modification is done in Arrhenius equation and introduced this part, which is T to the power m, and this activation energy E0 is basically the activation Arrhenius activation energy plus mRT. M is the appropriate power of temperature according to the system or according to the equation followed. So this is a limitation for Arrhenius equation, where we can see some non-Arrhenius behavior in some system or some process, like a glass forming liquid. This is an example where glass forming liquid, I have read somewhere that glass forming liquid shows non-Arrhenius behavior as the temperature is getting lower and lower. Then the equation shows very non-Arrhenius behavior, which doesn't follow the rules according to Arrhenius.
Yes, good. Next is what is catalysis and what the relation between catalysis, activation energy, and Arrhenius equation?
Okay, so catalysis is a process to fasten a reaction, or if in a reaction, we always in chemical kinetics, we always interested about the rate of a reaction or the speed of a reaction. So in case of predicting or determining the rate of a reaction, when a process is done to augment or to increase the rate of a reaction by adding some complex or adding some compound, that is called catalysis. And the catalysis, and in a catalysis process, the rate of the reaction is increased by adding the compound which is called catalyst. So what catalysts do? Catalysts do the role of the catalyst is to reduce the activation energy of the reaction and make another pathway to go through the reaction. So now, if we plot an energy profiling diagram, then we are plotting potential energy versus reaction coordinate here. This diagram is for an uncatalyzed reaction. But if we use a reaction with catalyst, then EAC, and this is EA. So currently you can see that EA is greater than EAC. This means the catalytic pathway reduce the activation energy of the reaction, and this is the process of catalysis by which we get benefited in case of increasing the rate of reaction.
Yes. Any drawback and limitation of these one? What the uses of these one in our society, human life?
In case of catalysis, catalysis always alters the rate and increase the rate. So when if a certain moment had come when we have to stop the reaction, or we have to change a certain extent about the pathway of the reaction, then it will be difficult for us to stop a catalytic reaction. Then we have to use some extra compounds which is called as catalytic poison or something else, like inhibitors. This type of compounds are introduced then when catalysis are creating problem in our desirable product or desirable reaction. So this will be the limitation for catalysis.
Yes. Next is what the main application of steady state approximation and equilibrium approximation. Explain 2-3 points.
Okay. So in case of steady state approximation, we can see that in case of a steady state approximation, the reaction, if a reaction which producing A producing B and then B producing C. So in this case, B is the intermediate here. B is the intermediate. This is K forward, this is K backward, and this is the whole rate constant of the reaction. So according to steady state approximation, it is assumed that the change of concentration of intermediate by very infinitesimally small time gap is 0. So in this case, if we make a plot, then this is the concentration of A and this is the concentration of C. But if you ask what is the concentration of B, then the concentration of B will be like this according to this graph. So when this type of case happened in a reaction, then we apply steady state approximation to find the ultimate rate equation of the reaction. So this is called SSA because we think that the intermediate is steady. The change of the concentration of intermediate at infinitesimally small time gap is 0. So by this approximation or the process of approximation tells us the actual rate equation of this reaction. So this is the main benefit or application of steady state approximation.
Yes.
So now we will be talking about the equilibrium condition. What is equilibrium condition? Equilibrium condition means that if a reaction which is in equilibrium with B producing C. So in this case, this is reversible reaction and this is very fast. So this A and B are in equilibrium. It is also an approximation process by getting to get the ultimate rate equation for a reaction which consists of multiple product like intermediate or something else. So this type of equilibrium condition or SSA like steady state approximation process are used to get or to calculate the final rate equation of a reaction.
Yes, good. Next, move on Lindemann theory and Michelmanson equation. Yes, what the difference of these one? Both. First of all,
Lindemann theory
application and difference.
So, sir, in case of Lindemann theory, at first it is said or it is assumed that the unimolecular reaction are always first order at any pressure range throughout the reaction. But Lindemann opposes that. Lindemann opposes by showing a calculation that when pressure range is altered, like pressure range is high or low, then the reactant, the concentration of reactant doesn't show always the first order with respect to the reaction. So in case of Lindemann theory, let's take A plus A, which activates itself, produces A star, and the rate constant is K1, and A star plus A, which produces A again, and the ultimate A star produces A. So in this case, first process is called as activation, second process is called as deactivation or decomposition. So in this case, we have to apply the SSA, like we will apply the steady state approximation to get the final rate equation. As we know, what is the rate? So the rate will be K3 into A star. So in this case, finally, when we determine the rate, then we see that K3 K1 PA square by K3 plus K2 into PA. This will be the final rate equation. And in case of high pressure, when PA is far more greater than K3 K1, or let's say it is called as K prime, then the rate will be equals to the first with respect to first order with respect to the reactant concentration at high pressure. But at the case of low pressure, then the rate will be vary with the square of the pressure of reactant. So at the case of high pressure, it will show first order activity, and at the low pressure, it will show second order activity. So at high pressure, it will behave like first order reaction, and at low pressure, it will behave like second order reaction. So this is the Lindemann theory, and from Lindemann theory, we can get the idea when a reaction, unimolecular reaction, takes place throughout the reaction at all pressure ranges, it is not always the first order reaction.
Yes. Any drawback and limitation of Lindemann and Michelmann?
Sir, for drawback, we have to say that in this case of Lindemann theory, it is not always correct that the reaction mechanism is taking take place like this reaction. So we have assumed this type of reaction mechanism pathway in case of Lindemann theory, but it is not always have to be the same pathway like in a unimolecular reaction. So this will give you a main limitation for Lindemann theory, and it further in further cases it doesn't explain for complex theories. So this is why Lindemann theory is not usable for all kind of reaction kinetics. So these will be the limitations for Lindemann theory.
Yes. Yes, what the main application of collision theory? Collision and activated complex theory. Both interconnected.
Okay, so in case of collision theory has some postulates that, and it is mostly eligible for elementary bimolecular gaseous reaction, where it assumes that the collision between molecules, perfect collision between molecules forms the product of a reaction. So in this case, according to collision theory, it assumes that the molecules are acted as the hard sphere, and it has to be collided with a certain energy. So first postulate is the particle is taken as hard sphere, and the particle should have kinetic energy greater than equals to the activation energy of the reaction. This means that the molecules which are collided to each other should have the kinetic energy which helps the molecule to get over the activation energy of the reaction to form the product. And the third postulate is there is a steric factor or there is a orientation factor. So the molecule should have to be oriented rightly before collision. Then it will form the ultimate product as we need. So this is the actual concept of collision theory, which further tells us that how a gaseous reaction, bimolecular reaction takes place and creates the product. So in case of collision theory, we will take KCT, and this is a modified equation, and this is K equals to P into Z into e to the power E0 by RT, where E0 is EA plus half RT, and EA is here the Arrhenius activation energy, and P is steric factor, Z is the collision frequency. This is the application of collision theory in chemical kinetics.
Any drawback or limitation of collision and activated complex?
There is some limitations for collision theory, and those are, it always have to be a hard sphere model. So if it is a hard sphere model, then it cannot calculate or it cannot take the actual shape of the molecule. So it just ignores the shape of the molecule and takes it as a hard sphere. This is the first limitation. And for complex molecule, there is a rotational motion, vibrational motion there. So collision theory just ignores those type of motion of molecules. And third, for complex molecules, which are basically multi-step reaction, so this type of reactions cannot be explained by collision theory. And fourth, this type of this theory does not acceptable for every type of reaction which occurs in solution phase or in solid phase. So these are the main limitation for collision theory in chemical kinetics.
Okay, what is salt effect? What the relation between salt effect and Debye-Lipkin limiting law, and ionic strength? Explain one by one the interrelation.
Okay. So, sir, salt effect in case of solution-based reaction, we see ionic reaction takes place there. So, in case of ionic reaction in solution, there is a effect which changes the rate of the reaction which is taking place in the solution. So what is salt effect? Salt effect is an effect which is introduced by introduction of another electrolyte, inert electrolyte in the solution based reaction. So there is a two type of salt effect. One is called as primary salt effect, and one is called as secondary salt effect. So in case of primary salt effect, we see that when we add a inert electrolyte in a solution where previously present A2 plus B3 minus, and we added some inert electrolyte which is M plus and Z minus. So we see that the rate of the reaction between A and B is increased. So if the rate of the reaction is increased by adding the inert electrolyte which directly affects the rate of the reaction, then it will be called as primary salt effect. And if on the other hand, secondary, so what is secondary salt effect? So in case of secondary salt effect, let's say A2 plus and B3 minus is reacting together, and OH minus is the catalyst in this reaction. So after adding some salt or some inert electrolyte which directly affects the production of catalyst, which increases the formation of catalyst so much that it will affect the concentration of the reactant, and the rate will increase or rate will alter. So it is a indirect effect, where in primary salt effect we see the direct effect of the inert electrolyte to the ionic reaction, but in case of secondary salt effect we see that the effect of inert electrolyte is on mainly the catalyst, and the catalyst then increases the rate of reaction, which finally increases the ionic strength of the reaction also. So this is called the salt effect of reaction, which is adding salt in a reaction and see the changes of the rate of a reaction. So now we will see Debye-Ukel limiting law and the equation which shows us that at how much extent a reaction rate is altered. So log K plus K0, K by K0 equals to 2 into A into ZA plus ZB into root I. So this is the Bronsted-Bejerom equation, BB equation. This equation directly tells us the effect of the salt effect. So shows us the salt effect in a solution-based reaction where the charge, which is dependent on the charge of the electrolyte which have been introduced to the solution, and it will also change the ionic strength of the equation. And what is ionic strength? Ionic strength is basically the strength of the strength does the ionic reaction or the reactant possess during an ionic reaction, which is